Chemistry is all about reactions. A reaction is a process of change in which substances turn into different substances. The Chinese for chemistry is shown here. The top symbol is the symbol for change, and the second one is the symbol for study, so chemistry is literally change study. A reaction changes substances known as the reactants into substances known as the products. We show this using a chemical equation. For example, our reactants might be hydrogen and oxygen. If we allow them to react together, the product we get is water. Notice that we use an arrow meaning reacts to make, rather than the equal sign you were used to from equations in maths. A reaction taking place is usually accompanied by changes which we can observe. These might include bubbles of a gas being formed, a substance with a different smell being produced, colour changes, an increase in temperature or a decrease in temperature, or light or sound being produced. Often we'll be able to observe more than one of these changes taking place at the same time. For example, if we fill a balloon with hydrogen and explode the hydrogen so that it reacts with the oxygen in the air to form water, we will observe light, noise, and we may be able to feel the heat given out by the reaction.
Nice. Right, we do a really big boy now. There's still quite a lot of nitrogen left.
Alright, let's do a big one.
To understand what's happening in a reaction, we need to understand that there are two distinct things happening. Firstly, the chemical bonds which hold the atoms in the reactants together are being broken, which takes energy. Then new bonds are being formed between different combinations of atoms to form the products. This process releases energy, which is what we were observing when the hydrogen balloon exploded. We've already seen the simplest type of chemical equation, a word equation, such as hydrogen plus oxygen react to make water. This is of limited use, and chemists prefer to use symbol equations, where each reactant or product is represented using its chemical formula. The symbol equation has exactly the same meaning, but it tells us about the amounts that react as well. Every 2 hydrogen molecules will need to react with 1 oxygen molecule to make 2 water molecules. We call this being balanced. You should be able to see that there are exactly the same number of each type of atom on either side of the arrow. 2 hydrogen molecules and 1 oxygen molecule contain 4 hydrogen atoms and 2 oxygen atoms. In 2 water molecules there are also 4 hydrogen atoms and 2 oxygen atoms. Symbol equations must always be balanced. This is really important because atoms are never created or destroyed during a reaction, just rearranged and bonded together differently to make new substances. Here's the word equation for the reaction between hydrogen and chlorine. They react together to make hydrogen chloride. Here is the symbol equation written out using the correct chemical formulae for hydrogen, for chlorine and for hydrogen chloride, but there is a problem. The equation isn't balanced. There are 2 hydrogen atoms on the left, but only 1 on the right, and the same is true for the chlorine atoms. 1 hydrogen molecule does not react with 1 chlorine molecule to make 1 hydrogen chloride molecule. To get the same number of each atom on each side, we add numbers in front of any of the chemical formulae. We can balance this equation by putting a 2 in front of the HCl, so that 1 hydrogen and 1 chlorine molecule react to make 2 molecules of hydrogen chloride. We are not allowed to change the chemical formulae in the equation to get it to balance, though. It would be wrong to write hydrogen chloride as H2Cl2 just to make the equation balance, because that isn't the formula for hydrogen chloride. One of the consequences of equations being balanced and atoms never being created or destroyed during a reaction is that all the same atoms are there before and after the reaction, just rearranged differently. This means the mass of the reactants must be the same as the mass of the products, because they contain exactly the same number of each type of atom. We call this the law of mass conservation. Scientists haven't always known and accepted the law of mass conservation, and indeed it does appear to contradict experiments that early chemists would have been familiar with. They knew that the mass of a candle decreases as the candle is burnt, and the same is true for burning wood or charcoal. They explained this with the theory that everything contained something they called phlogiston, which made it able to be burnt. Things that didn't burn, they said, didn't contain any phlogiston. The idea was that when something burnt, the phlogiston was lost, which is why what remained weighed less. This was a widely accepted theory because it fit the experimental observations well. In Paris, Antoine Lavoisier was experimenting with burning different substances. He noticed that when a metal was burnt, the mass increased rather than decreasing. Lavoisier was able to show that the phlogiston theory had to be wrong, and suggested, correctly, that when metals burnt, they chemically combined with something from the air. This explained why they got heavier after they had burnt. It was Joseph Priestley who figured out that it was oxygen in the air that the burning metals were combining with. We can see that when a metal such as copper is set up so that it has exactly 100 centimeters cubed of air around it, and the copper is heated strongly, then allowed to cool, the volume of air after the experiment is closer to 80 centimeters cubed. The copper has removed the oxygen from the air, combining with it to form black copper oxide. The law of mass conservation is an important one, and it is always true during chemical reactions. We can explain why the candle gets lighter and the metal gets heavier without having to break the law of mass conservation. When something appears to get lighter during a reaction, then substances are escaping into the air and not being weighed. The burning candle is producing gases such as carbon dioxide, which are escaping into the air. We could repeat the experiment with the candle inside a sealed glass jar on the balance. If we did this, the gases being produced when the candle burns would not be able to escape, and the mass would stay constant. When something gets heavier during a reaction, it is combining with something from the air, which was not weighed at the beginning of the experiment. Again, if we did the experiment in a sealed jar on the balance, the mass would not change.